Thanks. It's good to see a lot of familiar faces. Glad lots of people who've been before when I was here have come back again to hear this subject. So the first time I'm presenting in front of this group with a sort of Blockstream hat on, so it'll be interesting to see how that goes. You can tell by the artistically competent slides as compared to my normal fare. So I'm going to talk about a couple of things tonight. Previously, when I was last to address this group, I talked about some very short-term things, improvements in Bitcoin Core 0.11, and I also talked about some more airy philosophical things. Tonight I'm going to talk about things which are both longer term, but also a lot more concrete than the philosophical. So what I want to first do is sort of set a framework to understand the work that we've been doing here, and then talk about what exactly that work is. And a lot of what I'm going to talk about arose out of kind of thinking that occurred in this technical space of people working in the bowels of the Bitcoin protocol. How do we take this system with its design, and how do we make it scale and adapt, evolve to the greater needs of the wider world? And how do we do that in a way that doesn't push uncomfortable trade-offs onto people, doesn't change the system against people's will? And then, pondering that question over many years, some people came up with some interesting answers. And then we came up with another problem, which is, how the heck do we go build this stuff? Because it turns out solving a hard problem sometimes requires a lot of work. So one of the tools that we went to try to address that is why I co-founded Blockstream with a number of other technical people from the Bitcoin space as an organizational point to create funding and infrastructure to do some of this really hard long-term technical work. So these challenges I said I was going to talk about. I think it's important to really think about what Bitcoin is really set out to do in the world. If you think about the traditional systems of value transfer, traditional money systems in the world, they're based on trust. They're predicated at trust at all levels. And so you have to trust central banks to have good monetary policy. You have to trust banks to have good, secure accounting. You have to trust people to transport physical dollars and other assets from one place to another. And this trust works most of the time. But it doesn't always work. And whether it's working or not, it's expensive. And so this adds friction to the world's economy, and it diverts a large percentage of the world's GDP to other uses. And I think that money would be better spent in other places. So Bitcoin has a new idea to address this. And Bitcoin says, well, what if you take this trust-based system that we use for money all over the world and replace it with machine-enforced, computerized rules? And then maybe you can make some of these trust issues go away. This is actually fundamentally hard. We try to take information and build the money out of it. We find that information is very different from money. Information can be freely copied. Information is very hard to control. Information doesn't naturally have owners. And we can try to impose ownership on top of it, but those systems really don't work in a fundamental way. And so how do you go and build money out of information? How do you go use mechanical rules to build a monetary system? So Bitcoin answers that question. It uses a combination of cryptography and economics to go and build a system that we think does some interesting things in this space. And so we have the result being that we've built a system where the rules of the system have true force, where it isn't just that here's the rules and then maybe some people, if they like you, will follow the rules, but the rules themselves have true force because the algorithms are just enforcing them inherently by their operation. So this is great, so we can do something interesting, and maybe this is useful to the world, maybe it's a nice alternative. But the bad news is that we've built a system where the rules are in charge, and this is like sci-fi dystopia rule number 1, do not put the computers in charge. There's nothing as infuriatingly stupid as a computer, right? Nothing can be so dumb. But fortunately, what we've asked Bitcoin to do is very narrow. Keep track of these tokens in the system. And so Bitcoin is not going out and taking over the world, fortunately. But the problem that arises is that it's also not going and doing too much of anything else. So we're faced with this challenge where if we knew in advance everything that we would have possibly ever wanted Bitcoin to do, if we could see all of our problems, we could perfectly engineer our systems, make every component right, have no bugs at all, not just now, but against all of our needs into the future, then we really could have a system that really was just run by the rules, and there was no element of trust no aspect of depending on other people to make it go. But we don't have that. We have a world that's human, right? And we're limited by what human engineering can do. When Bitcoin was first created, the first versions of the system didn't even enforce ownership. You could spend anyone's coins because of a bug in how the return opcode was handled. So obviously, we couldn't take Bitcoin as it was on day one. It would have been over in 2010 when someone first noticed this. And so it has to evolve. But how do you evolve? So some people have sought to evolve the space of what cryptocurrency does for people by creating new cryptocurrencies with new properties. And this has a number of interesting results. But one pattern I've seen a lot with it is that it seems to have some fairly bad incentives, because often the motivation and mechanism in this stuff is to try to repeat the enormous growth of Bitcoin's value over time. And so there's a lot of energy that's put into the marketing front of this stuff, and really not that much energy put into the technology. So there's been a few altcoins that have done some really interesting technical things, but they're like 1/10 of 1%. And the rest are like, I copied Bitcoin and I changed the name. And that's not good or bad, it just is. This process has no natural stopping point, right? Today you have Bitcoin, then you have Fucoin, then you have Barcoin, then you have Bazcoin. And from the public, looking in at this from the outside, why don't they ask themselves, well, why would I use Bitcoin? It's going to be worthless tomorrow because everyone's going to use Barcoin or Bazcoin. And so you've seen this even with some of the more sophisticated altcoins. They're repeatedly forked over and over again. There's no stopping point. And one of the results of this is that it shakes confidence and this whole idea of making a digital money. And that's because really, when you think about why a money-like good is valuable, it's valuable because other people will accept it, right? It's network effect. And splitting it up damages the network effect. In any case, I've belabored this point now. I don't think this is a great way to solve it. It's a tool. I wish people that are trying that approach luck, but it's at least not where I want to spend my time. So if I'm not going to spend my time making altcoins, what am I going to do? Right? So from the very beginning, Bitcoin was designed to be extensible in specific ways. There's a very powerful smart contracting system that was built into Bitcoin from day one that allows the users of the system to specify rules for how their coins move. What you can do with this is bind Bitcoin into larger systems, and so you don't have to put all the features of the world into Bitcoin directly. It's a great idea. Unfortunately, the original implementation in Bitcoin had a bunch of bugs, but it's possible in a completely compatible way to fix those bugs and to improve its capabilities in a smooth way that doesn't interrupt anyone who doesn't care about those capabilities. We use this mechanism called soft forks, which are backwards compatible extensions of the Bitcoin protocol, and we've used them many times before. The most obvious example being the deployment of the 3-type addresses in P2S8, which was that soft fork done in 2012. But even with the ability to make soft forks to backwards compatibly extend Bitcoin, it's very difficult to make updates in a production system that people are counting on, that has $1 billion in value or whatever we're going to count with today. And many technical designs are much easier to do greenfield. If you have to fit things into the sort of shape that can work as a soft fork, it's much harder to design things. So when Adam spun back up in the Bitcoin space and got really involved again, he started talking about this notion of maybe you could extend Bitcoin using a concept he was just calling the one-way peg. Just you could create a new replacement cryptocurrency network and have it give you coins on it when you burn Bitcoins. Destroy Bitcoins, get coins on new Bitcoin. And this could be a mechanism to allow upgrades to the Bitcoin system in a way that wasn't coercive. If you don't want to upgrade, stay on the old system until network effect sort of pushes you over. But this one-way mechanism was a little lame in that you could only go in one direction. If it wasn't clear what direction people wanted to go in, if there were multiple new Bitcoins, which one was the true successor, then that's not good because you're then stuck and it makes losers, right? Now you've got some market speculation effect that would be good to avoid. So I added to this in late 2013 a way to accomplish the other direction, the two-way peg. And the idea for the two-way peg, which we've described in great depth in the Sidechains white paper, is to use the smart contracting functionality of Bitcoin to ask Bitcoin to validate a very particular smart contract. One that says, this coin has been handed over to the control of another decentralized network. And whatever that network says to do with this coin, then that's what this coin gets done with. And with this mechanism, you can move a coin into another chain, separate network, and then move it back again. You can effectively look at it like it's freezing the coin in one system and then creating a new one in the other and storing it and moving it back. So the whole idea of this is to gain the freedom and agility of multiple networks without rebooting the network effect. Now we can get all the advantages of being able to switch to an altcoin or whatever, but still keep the same currency. So we can paste the new, risky, experimental niche features off in separate networks. But unfortunately, making this work requires a great many moving parts. A lot of protocol design, a lot of worry about incentives, and a lot of details. And it wasn't stuff that we could do in just our spare time. So that's the company. So I'm very happy today to introduce a project that we're calling the Elements Project and Sidechain Elements. And what this is a project to advance the art for Bitcoin using really no holds barred, right? Exploratory technology. And using this Sidechains concept. So what we're doing is releasing a piece of free software, MIT license based on Bitcoin Core, and publishing it to everyone and cooperating on enhancing it. This software has many new and interesting features that I'm going to talk about some. And it uses the Sidechains mechanism to make it extend the Bitcoin ecosystem rather than being a complete alternative. Right now, the initial Elements network is this sidechain we're calling Alpha. And it is a BitNet testnet sidechain. So back in 2010, there was a parallel Bitcoin network that by social convention and a little more has no value. The testnet Bitcoin, many developers use it for testing their software. And so we've made a sidechain against testnet that people can use today. So I said elements. Part of the idea is not just to release the two-way peg mechanism, but to actually put it to some useful use, because without actual applications for it, it's just a bunch of cryptographic microcode, right? What are you going to do with this? Is this really useful to the world? And so we think so, and so we've put together some ideas. So I'm going to talk about these features that we've put into the Elements network, and you can think of each one of these features as just is basically one person's experiment, and with a bunch of other people helping out to make it actually work. And I hope that other people will pick this stuff up and run with it. And I do have to caveat, though, that this stuff is very raw, right? The whole goal here was to be able to experiment with low risk. And that means that we get the benefit of not having to do as much quality assurance. Right now, software in Bitcoin Core has to be basically bug-free. And Elements doesn't, right? It's a testing network. So I would suggest people don't go pick up this code and go use it with real value, or you may be sorry. And I may laugh. So the first of the elements I'm going to talk about tonight is the deterministic peg. This is the two-way peg mechanism that I was just talking about. It allows testnet coins to be moved into the alpha sidechain and back again. And it has some simple parameters. You start the move in the testnet network, 10 confirms happen on the testnet network. You go and tell the sidechain about it, and it takes 144 coins for the various timeouts to be met, described in detail in the Sidechains whitepaper. Now, although this has this two-way peg mechanism, it is not secure. And it is not secure because the testnet network is not secure. The testnet network can be very easily reorganized by anybody with a single ASIC miner or two. So it'll be interesting to see how this works under adversarial conditions as well. So one thing that comes up when implementing the two-way peg, as we described in the white paper, is that the existing smart contracts language in Bitcoin is no longer expressive enough to encode the rules to validate the return of coins. So what we're using in alpha right now is the procedure we described in Appendix A of the Sidechains white paper called the federated peg. The federated peg is a centralized mechanism that allows you to experiment with this sidechains without having to first go and deploy it in an actual network. So you can think of it as a protocol adapter. Basically, there's this federation of oracles, an N of M threshold, and you show the oracles the contract that you would like the network, the production network, to run, but it doesn't know how to because the smart contracting language isn't smart enough. And if that contract would return true, then the orc will sign. So it's a protocol app. And this means that the participants in this aren't themselves engaging in any discretion. It's just mechanical rules. If they misbehave, you can detect it, although you can't do anything about it. You can just, stop using that network. But as I said, there is this security trade-off, right? It's centralized. And if more than a threshold are compromised, they can steal all the coins that are in trust for the sidechain. In the case of alpha, we only have to use that mechanism for the direction of the sidechain back to testnet. The direction from testnet to the sidechain is directly verified by the sidechain network. It's asymmetric like this because we can very freely change the code in the sidechain. It's not as easy to change the code in testnet. Although there's some details with this. Right now, testnet doesn't have the compact proofs that we described in Appendix B of the sidechain white paper. And so the way it does this verification is by running a separate testnet node alongside the sidechain's node to verify that indeed the move occurred in testnet. And so this work, this deterministic peg implementation, is mostly Matt's design and work extending from the Sidechains white paper. He's here today with the blue hair. So the next element that's in the sidechain elements is issued assets. And actually, issued assets right now is just a pull request on our GitHub repository for this. It's in the pipeline. It's not merged into it yet at the moment. So the motivation for the issued assets, in my mind, is that Bitcoin brought us these smart contracts which are enforced trustlessly by the network. And this is great because often in the wider world, contracts are dead letters because the cost of enforcement is so high. You have a contract with your paper boy to deliver your paper and he doesn't, too bad. You're not taking him to court. Right? So the power of smart contracts is really that the network enforces the contract. And so enforcement's automatic and they can't be violated. This network acts as an impartial AI to enforce the contracts, and it's wonderful and great. And lots of people have imagined doing all kinds of fantastic trustless stuff using smart contracts. But a challenge with that is that the network can only do this trustless magical enforcement for things inside the network. Fortunately, the network cannot reach out into the wider world and change the ownership of physical goods. And so if you want a smart contract to arbitrate over things other than Bitcoin, you need to do something. And one way to address that is to represent those other things as assets, as tokens inside a common network that supports smart contracts. So you can imagine building things like fancy synthetic assets, an asset that is worth some component Bitcoin, some component in automobiles, using some smart property concepts. But you can't do that unless the network knows something about it. So there's this, in this space, there's the idea of color coins, which have existed and been deployed for a number of years, but color coins have some problems. In general, color coins are not SPV compatible. They're not compatible with the efficient verification in Bitcoin. So that means that the user of a colored coin has to trace the history of the coin through the blockchain, through all of its owners, meaning transferring potentially 30 gigabytes of data to hold the whole blockchain today and only growing over time. This doesn't work too well, especially if the user of the color coins is something like a smart property vending machine or a smart property car. You really don't want your car to have to download the whole blockchain to figure out who owns it. Color coins also encourage the creation of very tiny dust coins, transaction outputs in the network, that are a growing concern for the overall operating cost of the network. There's a trade-off with decentralization and cost that make that a little touchy. And the interesting thing is that a Bitcoin is valuable so long as the Bitcoin network exists and so long as people want Bitcoin. But an asset on a network is only valuable so long as the asset exists. It might have a very different lifetime. And with a colored coin, you have no mechanism to say that this asset is a different retention policy, different lifetime than Bitcoin. And so another kind of asset system could accomplish that. The main problem, though, I think, with colored coins is that they're invisible to the colorblind network. It's why they're easy to deploy, but it also means that they can't be made available to smart contracts to act intelligently on. Although there's a big advantage, I think, that people don't talk about enough for colored coins. They could be very censorship resistant because only the parties using a color coin know about the coloration. And if the color coin system was designed correctly, it could be utterly undetectable to the rest of the network. And so if other nodes in the network, if miners try to censor a colored asset, a well-designed color coin system could avoid that. Although current color coin systems aren't particularly good on the anti-censorship angle. So it's this issued asset feature. In Elements, what the pull request does is that it immediately adds all of the TX outs in the set of coins. It adds an asset type flat tag. And then this asset type tag is used to group the accounting rules in the system. So right now, the Bitcoin protocol enforces rules such as the sum of the input coins have to be less than or equal to the sum of the output coins. So there's just this making sure that the numbers add up, right? And so these rules can be grouped by asset type. So to say the sum of inputs of asset type X have to be greater than or equal to the number that come out. Fairly straightforward. And then to issue the assets, there's a new special transaction, and the TX ID, the transaction ID of that issuance transaction becomes the asset tag. So this is mostly the work of Jorge Timon, and this is all it does right now, but there's a lot more that it could do to be extended beyond that. So the next element that's in the Elements network today is this relative check lock time verify. So in the original Bitcoin systems, Bitcoin transactions have a good after date. This is the unlock time field. And that's somewhat useful, but many fancy contracts need something to prevent holdup. They really want to be able to create script hub keys of the form person A can spend or person B can spend after time X. There's a BIP65, which is in the works and maybe available this year, which adds an absolute check lock time to the Bitcoin network. And that's very useful. And that's in Elements as well. What relative check lock time is basically taking this a step forward. Instead of saying, having a fixed clock that coin will be spendable after a certain date, making that clock relative to another transaction. So the clock can start at one transaction and then finish after that. And this is necessary for some fancy protocols like Lightning Network to get really super scalability. So the way we accomplish this in Elements is that in Bitcoin there's a 32-bit sequence number per input to a transaction. The original idea was that you would increment this to indicate updated transactions, so you could revise a transaction. But there was no enforcement mechanism in the network. So you can update a transaction, but then the network could confirm an older version, which would probably be not what you wanted. And the network might do this because it could be much more profitable to confirm an older version. So because of that, people haven't used replacements in any real capacity in the network because it's insecure. Because there's no network enforcement of this convention. You have to basically trust the miners, to be honest, which they sometimes are and sometimes aren't, and people aren't really sure about when they can trust that. What relative check lock time does is it adds a rule so that when the sequence number is at its maximum, the transaction can be included at any point. If the sequence number is one less than the maximum, then the coin that it is spending must be at least one block old in the blockchain. If it is two less than the maximum, it must be 2 blocks old in the blockchain, and so on. And so if you start at a low sequence number and go up, what that means is that the later version of your transaction will be loadable into the chain earlier than the earlier revisions of your transaction. And so that gives us some real consensus enforcement. It's not a guarantee that the network will confirm the right transaction, but it means that the network will have plenty of opportunity where it can only confirm the latest version before it gets to the less recent or the less recent versions of it. So this is mostly the work of Mark, and he's also working on proposing this in Bitcoin Core as well. But it's available in Elements now. So the next element I'm going to talk about is one that has a kind of exotic name. And it's named this way to distinguish it from some other words we might use for it. I'll explain. So the name is segregated witness. So if you think about a Bitcoin transaction, a Bitcoin can be spent whenever some input, signature, is provided, which makes the script pub key return true. That's the criteria for spending coins. The network runs these scripts to verify that this is the case, and life is happy. It raises the question, what happens if you take a valid transaction and you take its inputs that are true, that you make the script return true, and you change them? You change their encoding, you change the values in them. This doesn't change what the transaction does. It doesn't change its behavior. It doesn't change who it pays. But in Bitcoin, doing this changes the transaction ID. And this seems like not a big deal, but it turns out to be quite a big deal. For one, it confuses accounting systems, which is annoying. But even knowing this, people haven't made their wallet software handle it particularly well, so that would be good to fix. But more importantly, when a Bitcoin transaction spends an unconfirmed coin, it's dependent on that transaction ID not changing, or it will invalidate the transaction. So if you have a chain of unconfirmed transactions, someone going and modifying the signature in one of the early ones invalidates the whole chain all the way down. And so the obvious thing to say is, well, don't make it possible to do this. It turns out, especially with the expressiveness of script, it is really hard to have rules for validating the signature which do not allow the signature to be changed. And in fact, cannot be done without reducing some of the flexibility of script. So there's a proposal, BIP62, which is rather complicated, and it basically says, if you make transactions that fit these narrow set of very common use cases, then we believe that the results with BIP62 enforced are non-malleable, that you cannot change the signature and result in another valid one. But we're not even completely sure if BIP62 is enough. So it's one of the reasons that BIP62 has kind of been stalling a bit. We've broken out some parts of it and taken it forward into the network. But BIP62 as a whole may eventually go in, but it's not a really crisp solution to this problem of malleability. So the name, where does this name come from? Well, if I talked about segregated signatures, it would cause a lot of confusion with the ECDSA cryptographic signatures as well. And when a Bitcoin signature is more than just the crypto part. It's the whole script validation. It's the set of inputs that make the transaction true. And so I'm using a bit of jargon here, right? A witness is a term from mathematical logic. It's used heavily in cryptography. And what it is a specific value that is a concrete existence proof for a claim. So if I have a function, and I say, there exists an x such that f returns true, that value x is the witness. So that's the signature in the transaction, is the witness for the transaction. And it's a good way to think about it, because Bitcoin itself doesn't care why a transaction was okay. Any valid signature is good enough for the network. The transaction will go through. It's also a good reason to think about the way Bitcoin works, because we know in a fundamental sense that it's possible to build, using fancy cryptographic tools, systems that allow you to build networks where you can validate their validity without downloading any of the signature data. You can get just a compact proof. When I say it's possible, that I mean this in a theoretical sense. It's not at all practical to do that yet, but maybe in 10 years it is. And thinking about in terms of witnesses to transactions helps sort of prime the thinking for these systems. The other thing that's important about this separation is that when you are validating, when you are downloading the blockchain, if you do not care to validate the signatures in the old parts of it, because you're just going to trust that the miners did the right thing there, then you don't care about the witnesses. You care about the inputs of the transactions because you want to know what coins are being spent, and you care about the outputs of the transactions because you want to know which coins can be spent in the future. But you don't care about the signatures. You're trusting that they're valid because they're 3 years old, and if they were invalid, maybe someone would have said something by now. And right now, in fact, if you go download Bitcoin Core, it skips verifying signatures deep in the blockchain for performance reasons, because otherwise it would take a week or 2 weeks to synchronize the chain. So it's a bit of a security trade-off in that it does that. But it still has to transfer the data, which is a little ridiculous because the witnesses, the part of the transaction that you don't care about if you're not validating signatures, is 2/3 of the data in the Bitcoin blockchain. So all this to say, well, the obvious solution to this is to take the witness part of the transaction and make it separate. So you have a transaction and you have its witness. So the transaction is split into 2 parts. They're always relayed together. But the transaction ID is a hash which only covers the main transaction part, not any of the signatures. Now the block itself still needs to commit to the signatures, to the witness. And it does this just by adding an additional level to the Merkle tree to put the hash of the witnesses in. And the reason the blockchain needs to do this is primarily for forensic reasons. If you have a 2 of 3 multi-signature transaction and the coins move, well, later you might want to go back and confirm, well, who authorized that move? And to do that, you need to check to see which of the signatures were actually the one used in the blockchain. So the result of this separation is that it is now possible, if you are not checking the signatures in the blockchain, or not checking all the signatures in the blockchain, to not transfer them. And this completely prevents unwanted, unintentional third-party malleability to transactions. And it prevents it in a way that we're sure that it prevents it, rather than one where we think and it only works for a subset. So this is mostly the work of Peter. So the next element that I'm going to talk about is some script enhancements. So as I said earlier in my talk, Bitcoin script was much more powerful, right? A little too powerful. It had the power to crash nerds and steal coins. So to remove this excessive power, many operations in script were disabled, which was really just a polite way of saying they were completely removed. But fortunately, the problems weren't hard to fix. Unfortunately, they were discovered in an emergency scenario. Instead of fixing them, they were removed. They can be restored in the network in a hard fork in a very straightforward way. Just turn them back on and fix the bugs. And a soft fork, they can be restored too, but it's a little trickier. But justifying this in the Bitcoin network is hard. You know, I'm very excited about fancy smart contracts in Bitcoin, more than most people I know. And there was a time when myself and Peter Todd were like 90% of the smart contract clunkiness in the Bitcoin network. But it's hard to justify something that has technical risk when no one is using it. And of course, no one's using it because it's not there, so there's a catch-22. There's also been, in the deep recesses of the technical community, a lot of very powerful ideas for new scripting systems which do things like make the scripts very easy to statically analyze to be sure that the script does what you think it would do, an important aspect of the contract. And there's a bunch of neat ideas to make things more efficient and so on. And maybe, it would be better to wait until those were ready. But the whole idea with this Elements project was to make experimentation cheap. So if experimentation is cheap, why not go fix the stuff in script? And so that's what Patrick did. And this set of features basically re-enables all of the disabled opcodes, the concatenate substring, the bit operations. It adds a few more fun things, like there's a deterministic random number generator that you can use in the script. And it added an operation to check the signatures of arbitrary data passed in on the stack, which is actually a very powerful feature because you can use that to build bonds for good behavior, where you can say someone can make a probabilistic payment, and if they double spend it, people can go collect their bond. And you can do that using this signature checking for arbitrary data. There's many things that you can do here. One of the ones I like is that you can build one of 1,000 multi-signatures where the signatures only take about 100 bytes in the transactions by building a Merkle tree that's validated by the script hub key. And if you can do this, then you can do things like put a small amount of Bitcoin on all of your servers with a different hub key on every server. And when a server gets compromised and the attacker takes the Bitcoin, you know which server was compromised because you can see which of the 1 in 1,000 multi-sig signed off on it.
Does this enable covenants?
It does not currently enable covenants, indeed. Next step, right? We also replaced the ECDSA signature with Schnorr. Schnorr is a different mathematical formulation for discrete log signatures. We're using the same curve as Bitcoin. But the Schnorr allows for a couple of improvements. One is highly efficient but non-accountable multisig, and batch validation, which gives us a roughly 2x speed up, which is nice. It also is the security proof for Schnorr, much more confidence producing. So speaking of signatures, there's another thing that we've done in Elements to improve signatures. So in Bitcoin, the only way that something like a hardware wallet knows the value of the coin it's signing for is if you send to the hardware wallet the transaction that created the coin it's spending. And the reason for this is because the only way that that value is committed to in the transaction is via the TXID of the coin being spent. And this is a problem because your hardware device may want to impose some policy, like actually telling you how much of the transaction is going to go to fees, or to control how much you're spending. So if you have to stream the inputs to the hardware wallet, you can create contrived cases where a transaction may need to have a gigabyte of data sent into the hardware wallet before it can validate what the value is of the coins that it's spending, which is ridiculous. And there's a very simple and straightforward fix that's quite easy to do in a totally new network, which is that you make the signature in the transaction directly cover the value, rather than only covering it indirectly through the hash of the prior transaction. So this was work that Glenn Willen did, and that's all we did. The signatures cover the values. So next element in Elements is a feature that is not something that would ever exist in the Bitcoin network itself. And I think this highlights one of the interesting ways to use this mechanism of the two-way peg and building other networks. is that you can experiment with ideas that are universally agreed upon as not very Bitcoin. So in Bitcoin, we have a decentralized consensus, hopefully, and it is essential for upholding Bitcoin's primary value, right, that it is a trustless system. If you get rid of the trustlessness, then you've got like PayPal that inefficiently implemented. So there's no debate or any confusion here. The decentralized model of Bitcoin is essential. What if you want to use the technology of Bitcoin to build a private system or a semi-private system? What if you want to build a low-value experimental system, small system? What does a decentralized system of 4 people mean? What is that? That's not decentralized, it's 4 people. And the mechanism that Bitcoin uses for decentralized consensus is very fuzzy, this mining mechanism. It's not secure when it's used at small scale. So even if you were going to build something decentralized, how do you bootstrap it? And many altcoins have struggled with this bootstrapping problem and have done a variety of things. So there are many other consensus models you can build systems out of that exist in the wider world. In the Sidechains white paper, we give a framework for thinking about the Bitcoin consensus model by describing it as a dynamic membership multi-party signature. And this is that the network is doing a threshold signatures where, kind of an N of M must sign off on the blocks. And who are the N of M? Well, it's a dynamic membership chosen by their own participation in hash power. So what if you replace the dynamic membership multi-party signature with just a multi-party signature, plain multi-party signature? Well, the result is a centralized security model, although one which is arbitrarily better than just trust one server. Because you can build a system which is real-time audited by all of its participants, and where most aspects of its behavior have machine decidability about their honesty. So you can say, are the signers behaving or are they not? I say most because, for example, you can't tell if they're censoring in a very clean, machine decidable way. You could build a system that has an arbitrary *** multi-sig policy. So you can say something like, blocks can be produced in this network if an auditor and 5 of these 8 parties or 8 of these 8 parties allow it. And the ** is, this is referring to the trust properties of the system. In order to decide if you want to sign a block or not, you need to first have a consensus. So if you had a policy, for example, that was like A and B or B and, or A and B or C and D, right? A pair or another pair, then that group could fork the network into 2 states because they were momentarily partitioned. And so not all policies make really good federated consensuses. So with this model, there's no human discretion required. You could potentially implement the signers in a federated consensus on very robust, tamper-resistant, tamper-detecting, self-destructing hardware. Some interesting opportunities there. As I said, this isn't a replacement for decentralized consensus. It's an extra tool we can use in places where decentralized consensus is not the best. And there are some applications where you need to have trust in any case. If you're building a system where all it does is trade around gold notes, and someone has to eventually redeem the digital gold notes for bars of gold, well, then you have to trust that issuer to do that. So maybe you can use that issuer as part of a federated consensus. Why not use it, right, if that trust is there? So this has been mostly the work of Jorge Colon. And it's something that we're using in Elements. And it allows us to have this Elements network be rather secure, even though right now it only has 8 users. Hopefully more than 8 by the end of the evening. So the next, and probably the most technically sophisticated feature of the set that I'm going to talk about tonight, is a feature that we're calling confidential transactions. So I've talked before about the importance of privacy in the Bitcoin sphere, and I won't belabor it forever. But I think that it's very important to have privacy in systems of value transfer. The traditional money systems have privacy. Right? When you make a bank transaction with someone, you know about the transaction, your receiver knows about the transaction, the bank knows about the transaction, but the whole world doesn't know about the transaction, unless the bank has very poor security properties. So this is like really table stakes stuff, and it's kind of funny in the Bitcoin space, we're so eager for Bitcoin to be successful, sometimes we wax over what a big limitation this is. But without adequate privacy, fraudsters can look at your financial records and target you. They can know exactly how to trick you. Thieves can go after the highest value targets, right? You go and make a purchase and somebody says, hey, this guy's got a bunch of money, I'm going to rob him. Right? This has incredible importance for businesses because your negotiating positions depend on what you can spend. Your margins are something that would be revealed if you were using Bitcoin exclusively. It's also important for fungibility, especially when we talk about things like federated consensus systems, which are not as decentralized. If you don't have enough privacy, then it's very easy for the participants of the network, even in the Bitcoin network today, to censor your transactions, and certainly in a system that was less decentralized than Bitcoin. And if coins are being selectively censored, you lose fungibility, which is an important criteria for money. So when talking about this, people go, but wait, Bitcoin's always got to be like this. It can't be private because Bitcoin is replacing the role of the bank. The bank can see your transactions, and that's how the bank keeps its records straight. And since Bitcoin is the role of the bank, and it's this public decentralized network, the whole public has to see your transactions so it can keep your records straight. This isn't true. It is completely possible to have total privacy and be completely compatible with public verification. And the easiest example for this is built right into every Bitcoin transaction. Consider a digital signature. With a digital signature, you prove you know the private key. But you don't tell everyone else your private key. That would sort of moot the point. So it can be done, we just need the right technology. So Bitcoin uses pseudonymity as its main mechanism for transaction privacy. But it's turned out this pseudonymity thing in Bitcoin has been really fragile. And it works, but it doesn't protect a lot of the cases that are important. When you transact with someone, because of your transaction, they usually know who you are. You go and buy a coffee. Well, in Bitcoin, it's very likely the person you just bought the coffee from can now see a substantial amount of your net worth information because of this transaction. So the pseudonymous address thing leaks all over the place, and users reuse addresses often, and it's very weak. And this lack of privacy in Bitcoin isn't just a thing that bothers bearded guys at the front of the room. This is something that comes up in every large institution that I've talked to about using Bitcoin and Bitcoin technologies. This lack of privacy is a major concern. And of course, I care deeply about transparency. People look at the public ledger as a way to achieve great transparency. But data isn't wisdom, right? This deluge of information in a public blockchain might tell you something, or maybe it's really misleading. True transparency requires a commitment to explaining things and helping people understand them. So, I don't think that we lose out on transparency by having better privacy. And then, of course, there's concerns about harmful uses. But it turns out that harmful uses happen already in a system we have that is very not private. Where's the guy that stole Mt. Gox's coins, right? Like, he's not in jail. In Japan. So the harmful uses still happen, even in a system that is conspicuously not private. And it turns out that people who are doing harmful things can afford to get privacy one way or another. They don't need the system to help them. But more than anything else, when I think about this subject, I think to the experience we've had with the internet in general. I participate in the ITF and work with many people whose beards are much grayer than mine. And there's this very widespread view now that we messed up. We, the community of people building the protocols of the internet, messed up by not making encryption always on, can't turn it off everywhere. And this discussion has come up in the ITF to apply crypto to more places many times throughout the years. And there's always been a reason to back off on it, make it optional, or put it in a corner, right? It's complex, it's slow, it's incompatible. And all the reasons are true. Right? All of these things are true. It's slow, it's incompatible, it's complex. But when we think about it historically, these are one-time costs or small ongoing costs. And we should have stomached them way back then. And the longer we go without fixing them, the harder they are to fix, the more dependence there is. There are whole industries right now that build deep packet inspection devices to insert advertising into your content on the internet, right? Like, it is what it is. I'm not making a moral judgment here, but they were able to exist because the internet did not have strong encryption. If the internet had strong encryption way back when, they wouldn't exist. And right now, they pay lots of people to go to standards bodies and to fight against crypto on the internet. This isn't the place we should be. This is a mess. So I think about this and I say, well, if Bitcoin were really in this fantastic future to have displaced other systems of money in the world, but I want to live in that world. And no, not unless we improve the privacy story. So what can we do? I'm not the only person concerned about this. And there have been many people working on privacy in the Bitcoin space, many other proposals, some of them mine. I group them into two sets, compatible and cryptographic. So compatible solutions are things that you can do in the existing Bitcoin network today without modification. Coin join, coin swaps, centralized privacy servers. The compatible solutions are nice because they're immediately usable, but the privacy they provide is often very fragile, usually due to people being able to trace the amounts. If, X Bitcoin come in and then exactly X come out, well, then it's a pretty good guess that it was just the same user on both sides. The cryptographic solutions generally have a different set of problems. So this would include things like zero coin. There's a proposal on Bitcoin Talk that most people have never seen called one-way aggregate signatures, another cryptographic privacy technique. There's the traceable ring signature approach used in Bitcoin and Monero, or Zero Cash. And the cryptographic solutions, universally, have this problem where they break pruning. So in Bitcoin, to validate a new block on the network, you don't need to know the whole history. You just need to know a small summary of the history. And you can forget the rest of the history to validate a new block. This is critical for having good scalability in Bitcoin, because you don't want to have to do a random lookup to the whole history to validate something. The cryptographic solutions for privacy hide which coins have been spent, and in doing so, they break pruning completely. They also often need new cryptographic assumptions, although that's not true for the traceable ring signatures. They often have very poor performance, or they're just not implemented, very complicated, right? And people haven't done them yet, or they're keeping them private because they want to make an altcoin out of them, or whatever, right? So, let's take a step back here. The prior work on cryptographic privacy has focused on the transaction graph, making the transaction graph private. And this is actually a little odd when you think about Bitcoin transaction privacy from the framework we use to think about internet protocol privacy. Because the transaction graph is really the metadata about the transaction, whereas the content of the transaction is the destination and the value. Now, it's very important to keep your metadata as private as you can, but keeping metadata private is often a losing battle. It's very hard to do. It's very expensive to do. So generally on the internet, except for things like Tor, the metadata is not made private, but the content is made private. Well, what if you do just make the amounts of the transaction private? The destination of the transaction can be made private very easily by using the pseudonymous addresses or techniques like stealth addresses. What if the transaction amounts are made private? And I think if you think about this, it actually is the case that the amount is what needs to be private more often than the transaction history. And also, if the amounts are private, all of these other schemes in the compatible class, things like CoinJoin, are tremendously more powerful because their weakness comes from tracing the amounts. So if the amounts are private and they can't be traced, CoinJoins are all perfect. So the approach that we've taken for this, that we're calling confidential transactions, is to replace the values of Bitcoin amounts and transactions with these 33-byte commitments, which you can think of like a cryptographic hash, a keyed cryptographic hash. But the commitment scheme we're using preserves addition, meaning that you could take a set of commitments and add them up, and you get the commitment to the sum of their values. And with that property, the network can still verify that the amounts of the transactions add up, that you haven't created a coin out of nowhere. So this was originally proposed by Adam Back, my co-founder, in 2013 in a Bitcoin Talk thread called Bitcoins with Homomorphic Value. His original proposal was a little bit technically dense, and it took a bit of work to make it sufficiently efficient, mostly because of this one problem. When you take a set of coins and you split them to create multiple outputs, the system can easily verify that the sum of the inputs is equal to the sum of the outputs. 1 plus 2 is equal to 1 plus 2, right? That's the thing it can easily verify. But unfortunately, 1 plus 2 is equal to negative 10 plus 13. If you have a negative value, it still adds up. And so the system has to make sure you can't make transactions that output negative amounts of coin, or you can create coins out of nowhere. And so what you need is something called a zero-knowledge range proof. And the zero-knowledge range proofs that we have are linear in the size of the values that you're expressing. So in order to make this stuff efficient, I invented a generalization of ring signatures, which I published about last week as Bromian ring signature paper. And I use that as a building block to build a very efficient range proof system. And I believe there are many range proof systems in the literature, but I believe mine is the most efficient one yet described. And what this allows you to do is to prove that a value is within a particular range using about 2.5 kilobytes for a value which is 32 bits in size. And I made the scheme flexible so you can choose how much of the value you're keeping private. But this is still a fair amount of data to add to a transaction. So the next thing that comes into this is the segregated witness part of the system. Because with segregated witnesses, these range proofs don't have to be part of the data that you're validating forever historically. And then I came up with a cryptographic trick that allows you to, without adding any more size, it allows you to reuse that. It allows you to reuse about 2 kilobytes of that 2.5 kilobytes to communicate a private message from the sender to the recipient. And people often want to put messages like refund addresses or invoice numbers, delivery addresses inside Bitcoin transactions. And it's a little hard to stomach that on a public network that's adding cost to everyone. But it can be accomplished as a direct side effect of the range proofs. Just slipped in, adding no extra size to them, which is pretty neat.
Do you suspect this can be improved further?
I suspect it can be improved further. Although, I did work quite a bit on this. So, I also have a technical write-up that I'll publish tonight that talks about all the techniques that I used. The proofs are actually decimal floating point numbers, so they have an exponent that's separated non-private. They're encoded in a mixture of base 4 and base 2 because reasons. And all built on top of a ring signature scheme that's more efficient than any before it. And so but I think it can be improved further, and I intend to work on improving it as it becomes possible to do so. So this whole scheme is compatible with transparency. You can use it to have watching wallets. There is basically a watching key associated with a wallet. You can share, and if somebody has your watching key, they can see all of your values without being able to spend your coins. You can also share the blinding keys used for individual transactions. So you can prove to someone a payment had a specific value without revealing anything else. So this has been the project I've mostly been dealing with. I've had a lot of help from a lot of other people. So, some future direction stuff. All the stuff that I've talked about tonight is highly experimental. It's at varying degrees of maturity, but definitely experimental. So I'm looking forward to see what interesting and informative ways it will blow up and catch fire. I know the testnet itself has been getting some interesting attacks lately as well. So I and the other folks that have worked on this plan to continue to refine these proposals and work on other ones. Some of them are suitable for use in Bitcoin Core, and we'll mature them and hopefully get them out there with the experience of actually running them in a network. As far as the whole Elements project in general, there's a question. Will having this Sidechains mechanism and this testbed to do things, will it result in a community that builds new technology? Will the fact that we can work on the system without rebooting the network effect, without seeking permission from anyone, create your own sidechain, right? You don't have to ask me to do it. Will that result in more development in this space? I'm not sure, but I look forward to finding out. Thank you. So the two questions are these different features separate sidechains? And no, they're not. We've dumped them all into one. And there would be many reasons to make them separate that would be nice, particularly when they fail. It would be easier to figure out exactly why they failed. But the problem is in running any network, we know from the work we've done on Bitcoin, is just a tremendous amount of work in monitoring it and maintaining it and running nodes for it. And so it was easier for us to just put them all into one system. Maybe this was a mistake because we've suffered a lot from the integration work actually. A lot of these changes conflict with each other in the code base. The second question was related to the confidential transactions, and basically, is it compatible with having the publicly verifiable, transparent ledgers? And it absolutely is. For one, you can just not use it, but the other is that you can publish to whomever you want your watching keys for the wallets, and so and that you can publish them to the world, or you can publish them just to the auditors, right? You control them. Back there.
Sorry, have you published what of the nodes of the the one that is called Sidechains? Can we see the code already?
Yes, so can people see the code for it? Yes. So where can they get it from? Is it from the Block? Can you click on the Blockstream website to get to it?
Yeah.
By the time you get to a computer, you will be able to go to the Blockstream website, and it will link you to a GitHub page, which will link you to the Elements project GitHub page, which has the code for all of it, and you can download it and use it and do crazy things. Yeah.
Project elements.org doesn't work.
Oh, project elements.org. Great, that works now.
No, Elements Project doesn't.
Oh,
That's right.
Oh, elementsproject.org, is that correct?
Yeah.
Thank you.
So I didn't get clear answer last time. So when you transfer some bitcoins to the sidechain, you need to log them on the bitcoin's blockchain and then unlock. So how bitcoin blockchain will know the rules for individual should unlock?
Yes. So the question here is, how do you do this? How does the Bitcoin network know the rules in order to allow unlocking it? Right. So today the Bitcoin network doesn't, and the testnet network doesn't. They don't know the rules to do this for anything. And so the way we're accomplishing this for the Elements Alpha sidechain is with this mechanism described in Appendix A of the Sidechains white paper called the Federated head. So there's external workers that are these trusted centralized parties that sign off on it. It's a trade-off, but it allows immediate deployment. That's why I can, tell you something you can go and download and use today, rather than some bit that may get implemented 5 years from now.
Can you guys wait for the mic, please, so everybody can hear your question? Thanks.
Hey, Greg, I was just wondering, has there been any more progress made on atomic swaps since you published the white paper?
So the limitation that atomic swaps suffer is that the atomic swaps, to be secure, need refund transactions. And refund transactions are vulnerable to malleability. So there's another way to do an atomic swap without a refund transaction, and that's using the absolute check lock time verify. So I think absolute check lock time verify is making nice progress, is a good proposal. And I think it's on track for deployment this year. It had to wait for another proposal to get locked into the network. So I think once those are out there, we may see more activity in atomic swaps, but it's hard to say, because you could do them today with just reduced security, and people aren't. Of course, they could be done on the Elements network immediately if you wanted to experiment there as well. So maybe some people that are holding off developing atomic swap software because they can't be used securely on Bitcoin might be more inclined to play with them on Elements where there is a check lock time. But I'm not sure.
Hi, Greg. Any thoughts on legal implications of federated text? Are they built into their own?
It is complicated. My system is a testnet network. That makes it a little less complicated. Talk to your attorney.
When it comes to when it comes to the two-way peg and returning points from the sidechain back to Bitcoin with the, let's say it'd be an opcode that does the SPV proof verify. My understanding that like an SPV wallet has block headers from the Genesis, all the way from the Genesis block. So with this, the opcode that returns side coins back to Bitcoin have to verify the entire sidechain blockers.
So one of the appendixes, I think it's B, in the Sidechains white paper is a scheme for compact SPD proofs that basically allow you to show that a particular blockchain has a certain amount of work in it without revealing all of the headers. It has logarithmic scaling. So that's something we don't have implemented today. So we have a script opcode that does the proof verify. It's used in the direction of testnet into the sidechain, but it's not used in the compact SPD proofs yet. We just haven't implemented it. There's a bunch of free parameters in the design that we've been debating over for a long time. But there is a scheme to make it very efficient and keep the headers out.
Hi, can I just quickly ask about your concerns around privacy? Because I was a little sceptical of some of the arguments. Firstly, numerous people will have, the vast majority of us will have lots of different key pairs, and so we'll use a certain key to pay for small transactions and keep another key pair to hold our savings. So I don't really necessarily see the concern around me buying a coffee and therefore the coffee shop knowing exactly what my total bill is. A number of your other arguments, firstly there are rich lists, so we have lots of information about multi-millionaires, multi-billionaires, people can see that they have nice cars, nice houses. I don't necessarily see why, even in today's society, we can see which people are wealthy and which people aren't. And again, your arguments around this being a problem for negotiations, I don't really see that if someone has a budget, they don't necessarily have to pay their whole budget to buy a specific product or service. Like, why is that necessarily a concern in negotiations?
None of these things make clear line rules, right? It's not like when someone can see all of your finances, you can no longer negotiate. But every trade we make is along a continuum, and there's a cost associated with it. So there will be some difference in the amount you would pay when your opponent has more information. And people don't have to have that promiscuous transparency. They can just go use alternatives to Bitcoin. And so if you can save money by using other systems, then why not use them? It's a disadvantage, even if it's a small one. So I don't necessarily feel I need to debate the details, although I think it's a bigger one than we're crediting it for. Like this notion of people having separate addresses. In this room, maybe quite a few people have separate addresses. In the Bitcoin space in general, people aren't keeping their finances separate. It's very difficult to do that. And even when you're a very technically sophisticated user, I think I qualify as one, I've made many transactions that revealed a bunch of information about my finances accidentally, because it's easy to mess up. People can make reasonable inferences about which coins were spent together or which addresses were used there. And then there are things like data leaks, where there's a tremendous amount of my personal financial information made public by someone else's information being leaked out. And so these are all things that are made better by having better transparency in the system, or better privacy in the system, even if it's not perfect.
For the hiding of the announced stuff, that still leaks metadata information about what the inputs were and what the outputs were. Right?
Yeah, because you learn a little bit about the values in two ways. One, the range proofs themselves prove that it's in a range, and you can make the proof smaller by making the range smaller. The other way is because obviously if there were plain text values somewhere in my history, if there was only one Bitcoin that went into this graph of transactions, then my output could only ever be as much as one Bitcoin, right? So there's still some information there. The key thing to keep in mind, though, is that if these confidential value transactions are used with coin joins, then the set of the coins coming out of the coin join have the range, the plausible range of basically being any of the sum of all of the inputs. So it can get pretty anonymous pretty quickly.
I have a quick question. With the watching keys, are they revocable, and can you tell who has them?
No, not today. That's an interesting question. When I said I thought there were areas to improve, one of the things that Adam and I have been working on for some time is in the context of stealth addresses. One of the problems with stealth addresses is this is a scheme for basically getting a one-time use address every time you transact, but having a static address that you give people. One of the problems with stealth addresses, you can ask other parties to scan for you. You can give blockchain.info your stealth address private key, and they can scan for your transactions, which is convenient, but they can always keep scanning for your transactions and then give away that key to other people. So for stealth addresses, Adam and I had come up with some schemes that use some fancier crypto that allow you to delegate for just finite ranges of blocks. And those same schemes could be applied for watching wallets as well in this confidential value scheme. So potentially you could make a watching wallet that was good only for a certain range of blocks. And maybe that moves more in the direction of having control over that. But it's an open area to explore. And until you asked about it, I hadn't thought about it from this particular use.
Yeah, the Revoke SSL guys came through and they talked about having a local service.
Mm-hmm.
You have sort of a mechanism like that where are you familiar with it?
Yeah, yeah, there's things that can be done here. But more room to experiment. Like, this isn't a finished proposal, right? Like no one's saying go and put confidential value stuff in Bitcoin today. This is a very raw new system that needs to be analyzed and understood and optimized.
Great. Have you thought about how to indicate for a given address what chains there might be relevant value?
Yeah. Right now we're not doing anything really smart with that. there was a scheme that we'd come up with to allow registration of addresses in multiple chains. So you could basically have an address sign off on, like, I'm willing to accept coins in all of these different chains. And then you could, if you understand those chains, you could pay to those addresses. One of the nice things about it is that this can be done with standard Bitcoin addresses. So I give you a Bitcoin address, and if you are also sidechain aware, you could automatically pay me on a sidechain that we share in common. But that's not implemented in this right now.
So when the question regarding the two-way peg, if it's not used with centralized or federated oracle, do I understand correctly that the main solution would be merge mining? And if yes, what percentage do you anticipate would be needed on a sidechain network?
So I think that the real challenge in that question is how do you get security right? And nothing about the sidechain's proposal demands merge mining. It's an option. Although not merge mining, then the question is, well, do you merge mine or not? The question is, can you merge mine and give you more or less security? We know from Namecoin that when Namecoin's whole subsidy return in real dollar value was half of what transaction fees are today on average in Bitcoin, Namecoin achieved something like 80% of the Bitcoin hash rate. So I think that's evidence to suggest that if the software ecosystem around merge mining were done particularly well, that very high hash rate could be achieved. Is merge mining acceptably secure? That's an extra, more complicated question that deals with incentives. And it's a very hard question to answer because before you can answer that one, you have to answer the question, is Bitcoin secure? And particularly, is Bitcoin secure not today, but in the long run? Because right now, Bitcoin security is propped up by the distribution of subsidy. The subsidy is going away over time, and what Bitcoin looks like in the future, where subsidy is not providing the security, is an environment much closer to the thing that you get right away with a merge mine sidechain. So that's still an open question, sort of feeling out all the trade-offs there.
Next question.
I'm going to like to ask the same question. Have you given any thought to handling inflation on the return to Bitcoin? Like if the elephant's sidechain is, if every block is 100 Bitcoins forever.
Yeah, it could be done, right? So you notice the name of the two-way peg feature in Elements is Deterministic peg. And what that's really referring to the fact that the mechanism that controls the value ratio between testnet and alpha sidechain is really any deterministic function, anything that the networks can compute. So you could imagine creating a sidechain that like had inflation in the sidechain. It's just that the coins in it would be increasingly backed by less and less Bitcoin. So if you move coins back, they get less Bitcoin behind them. So some of my co-founders created an altcoin called Frycoin, which is an inflationary cryptocurrency. It has a bunch of interesting ideas behind it. And nobody uses it because they're not really enamored by this inflation, I guess. But maybe it's really ultimately a better design. And I don't know how to deal with the fact that maybe there's a system which is in some economic sense superior, but no one wants to use it and they can choose not to use it so they won't. Because I think that'll also be the case for things like sidechains that are created that have like inflationary ratios, that people would choose not to use them because why am I going to put my coins in a chain that gets less valuable? Who knows?
Well, I mean, even if it was deflationary, if every block 10 random coins was just deleted.
Yep.
So the return.
I want to see that. Well, I mean, I have to say, like, that may be the one we already created.
Don't worry, just test that.
Yeah, it's testing.
In one of your slides, I think it's correct when you mentioned that you were talking to the industry and saying this is where the blockchain about Bitcoin. Can you shed any more light on what those examples were?
So talking to people that want to look at, there's basically two areas that I've seen this in. I've seen this people talking about tracking other kinds of assets and like equities and things like that in Bitcoin-like networks. And there are all kinds of complexities in doing that. They make it advisable or not. But in any case, one of the concerns that comes up is the commercial confidentiality of that stuff. And in general, when just talking about it in terms of as a remittance and payment system, it comes up as an issue, the conspicuous lack of privacy. And maybe the people I'm talking to are just mining for weaknesses, because it is a weakness, maybe not the greatest. But I thought it was interesting that it isn't really just in the Bitcoin space, the people that speak the most about the sort of privacy area are the people that are being super transgressive. You expect to have a Molotov cocktail on the other hand, right? And really, I don't think that this is that political a thing. It's a normal feature that financial systems have.
Can you talk a little bit about what the future will be? What do you like to achieve in the next 6 months to 12 months on these sidechains payments?
Well, there's a couple of things I'd like to achieve. Some of the ideas that we're working on in this, like the relative blockstream stuff, I'm sure things that people will crop up with and want to try out, are relatively straightforward, and I'd like to just pipeline them into Bitcoin. If they're designs that people like, they can be shown to be safe and good and useful. And I think that would be a success point to show that this actually can incubate ideas for the regular network. I'd like to also see use of this to try even further out ideas and the kinds of stuff I'm talking about here. An area that we didn't really explore other than segregated witnesses is in improving fundamental technological improvements to scalability of the system. There are many ideas that I published about for the last 4 or 5 years. They're too aggressive to do Bitcoin. Even think about doing Bitcoin right now, without even trying them out. And so I'd like to see those tried out in the system. But more than anything else, I'd like to see participation. Right? It's an unanswered question I have right now is why isn't there more technical development in this space? And there are many reasons that hold back technical development. Cryptographic protocols are super hard. The number of people that know about this stuff already is super small. Many of the people who are knowledgeable about this stuff think of Bitcoin as a Ponzi scheme, but that's getting better over time. And then there's the allure of altcoins, right? Like, why would I go work on stuff in the Bitcoin space where maybe I can do an altcoin and make a bunch of money on it? Which is kind of attractive, right? But I think that that's petering out somewhat. And it'll be interesting to see how it evolves. So I want to see what the participation is like. And will this be a tool to sort of jumpstart more public development on underlying infrastructure? But I don't know.
Yeah, you already mentioned the problem, the potential problem in the future when the subsidy runs out. So, in the future, in 25 years, basically, if the total value of Bitcoin is X, whether it's 1 billion or whatever, I don't know. But still, the amount of money spent for mining should be only a small fraction of it.
Right.
Yeah, and then again, the money that would be needed to tax Bitcoin would also be basically this fraction, and that is a potential problem, I guess.
Right.
Do you see a solution to this problem somewhere within the Sidechain project?
Well, I think that in the Sidechain project, we may gain the ability to experiment with other ideas, and that's the most I can say that it can do to help this problem. But I think that's actually one of the biggest challenges right now, is experiment in a place where you're not off starting something totally new that has its own failure modes because it's new. Right? There are many interesting altcoin ideas that have failed not because their technology was bad, but because network effect. You want to start a whole new thing, like you have to sell both the currency and the technology. So I hope that they'll help there. As far as that problem in general, well, for one, it would be a good problem to have these minimum value Bitcoin in the future, where this is a real concern. And I believe that if it is that case, if Bitcoin is very valuable in the future, that solutions will be developed so long as we have a mechanism to go and develop it. But I don't have answers to that. And it's one of the big unanswered questions.
Hey, Greg. I have a question around what are the plans? Do you have plans to develop other industry or vertical specific chains, or are you going to lump all of these into one chain? The other question is, like, if someone who wants to use chain without chain, how would that integrate?
Yeah, so one of the nice things about sidechains is a concept, is that they're independent. And so separate networks can coexist and transfer funds between each other by going between the Bitcoin or testnet network in between. So there's nothing wrong with having more of them. I suspect that, at least my vision on sidechains all along has been that it's likely the case that there will be something like a power law distribution of networks in the future, where there are some smaller number of networks that are very widely used, that have the features that most people care about, and then there'll be lots and lots and lots of niche and experimental things that are not used by as many people. But I'm not sure. That's just a guess. Let's see. What else was there? Yeah, I mean, someone can take the sidechain element software, start another chain with it, like download the software, create another chain. I'd be glad to include it in the project. I'm not sure how that will pan out. It depends on what the participation looks like. So I'm looking for open participation. So, but we'll learn what it exactly will look like.
For the deterministic pseudo-random number generation.
Yes.
What is seeding that, and is it powerful enough to allow Sidechain style proof of still having a base in it?
It could potentially be used for that. Yeah. So what's seeding it is input that comes in off the stack, and so any way you can get data into the transaction via other mechanisms, for example. Like
can it use a specified block number as an input?
Not currently. Well, sort of. What you can do right now is you could, using the existing opcodes, take a block header and validate it, and use the hash of the block as the seed for the random number generator. But it's a little ugly. Patches accepted. Yeah, what the random number generator is, it's basically just it's an opcode that takes an upper and a lower bound, and it efficiently runs SHA-2 with a seed to produce a number in that bound, uniformly distributed. And the seed is up to the script.
So, question, it seems like you put a lot of thought into fixing the perceived limitations and design flaws of the Bitcoin technology stack, and there's some very interesting possibilities here. My question is, have you thought about other altcoins? Some of them are very different, of course, but any thought given to compatibility with sidechains with other altcoins?
So, depends on how you divide it up. I think it would be not entirely fair to say, but I could say it's immediately compatible with the vast majority of all altcoins because the vast majority are just copies of Bitcoin. And there are some altcoins where this whole area of design is compatible with it, and some where it's not, depending on their smart contract design. In terms of some of the other things I talked about as well, I mentioned that I made a generalized ring signature scheme, and I've already pointed this out to the developers of the Monero cryptocurrency that uses ring signatures in a different way for privacy, because it would have, the scheme I came up with would have the size of those signatures. So I'm not really sure how it'll fall into that ecosystem. And I have to say that because from just a first principles perspective, I'm not too excited about the altcoin approach to solving flexibility in the cryptocurrency space. I don't track it maybe as well as I could or should if I really wanted to be up to date with how it would fit into that ecosystem.
That's great. I have a question. In terms of pipelining the features from elements sidechains into Bitcoin Core and gaining participation among developers, could you please maybe perhaps tell us a bit more about Blockstream, the company, and where do you see it in 10 or 20 years? What's the business plan of Blockstream?
Yep. So in the case of Blockstream, the company, our business is really focused on building trustless infrastructure and taking the technology in the Bitcoin space to the wider world, as well as improving it for Bitcoin itself, and building businesses on top of that. So doing things like bespoke sidechains for various applications, doing consulting work in some places. So there's a whole spectrum of businesses that we can be doing on top of this on infrastructure that could be built if the base infrastructure were good enough. And so I think there's shared interest in improving that. We'll see how it pans out.
Next question. Come on, guys, that's noise here.
if the sidechain upcoder gets implemented in Bitcoin Core for whatever consensus disputes like that, would Elements ever operate on its own as an alt? And actually, follow-up question, can Elements operate as a parent chain with its own, sidechain SPV verify operation?
It theoretically could, I'm not sure, certainly it can be made to, right? It's not done software. So the answer is always yes, it's like change it and they can do it. I mean, I don't have any interest in creating an altcoin out of this for the reasons that I said before. Actually, one of the jokes I was making before our release is that we should have an office pool to bet how long until an altcoin is like built out of this stuff. Although I'm very afraid for anyone who tries that because the software is not very mature at this point. So I think people will do this. And it isn't specific to Elements, right? When we created the P2SH functionality in Bitcoin, it took us months to mature it and get it deployed. The first versions of it were flawed and could exhaust memory on the host and had all sorts of bad vulnerabilities. It took us a number of months to get it to the level of maturity where we really could deploy it in Bitcoin. During that time, an altcoin arose that basically advertised it had this great new feature set, which then copied the description of P2SH, and it was announced with exchange integration on the first hour of its creation. Which is what it is. It's maybe a little disappointing to work on something cool and then have someone competing with you using your own code. I mean, this is the case. This is what it is in Bitcoin. It's one of the prices of free software. And I think that the flexibility that the software does not have inherent, the fact that the software is free allows people to do this, but it must be free if it's to give the users the freedom they need to trust it as a currency thing to handle their money. So I do.
Okay, and if that's all we have, I'll wrap it up for tonight. Everybody, thank you so much for coming out. A warm round of applause for Maxwell.